I just want to give you some exercises to do. Very simple, and then I'll give you the solutions. In fact, they're on the paper. Compute the world line for circular orbit around a spherical mass like the Earth. Compute the world line for a particle in that Earth tunnel. Okay, you dig a hole through the Earth to the other side, and you just let it go at the surface, and then it goes down, and what happens to it? And also for a particle that's infalling, you let it go above the Earth surface, you just let it go at some height, and it's falling through, of course, neglecting air resistance and so on. So those three are three simple cases of free fall. It's falling towards the Earth through no atmosphere, right? It's in free fall, it's not resisting anything. Second case, it's in orbit around the Earth, and you can make it, for example, at the radius of the Earth, so skimming the surface of the Earth in a circular orbit. And the third one is the tunnel going up and down. Okay, just try it for a few minutes, and then I'll give you the solutions. So basically what you're looking for, when you're looking for the world line, what are you looking for? R of t. The curvature of the world line, R double dot. R of t is simply the graph in this x plus t axis, so we call that the world line. It's just that one-dimensional graph.
Is the world line.
Right, or x of t, or y of t, or whatever.
You want to find R double dot?
R double dot is the curvature of that world line. So find first R of t, and then find R double dot.
So if we do like the orbit, should we do it in free?
You can take, okay, those are very good questions. Take the simplest possible way of solving it, just so that you get the answer. In other words, you don't need to do it that way, right? That's what you're saying. Just everything, choosing your coordinate frame, your coordinate system, and your reference frame, and so on, the simplest possible way.
So in terms like this orbit one, what would you want it? Like, what sort of coordinates?
Choose. Okay, that's a good question. Choose the coordinate system that is simplest to use. Namely, spherical coordinates.
Okay. That makes it a little easier.
The world line of a circularly orbiting particle is obviously a helix. It's just going like this. Okay? Take a helix. All right? So this is R of t for any orbiting particle, the Earth around the Sun, the Moon around the Earth, etc. All right? So basically, this is the world line. Okay? So this is the world line of a particle. This is the time axis. All right? This is the xy. All right? So R is simply along here. At any point along the time axis, the distance in the xy plane is the same. Okay? So we just call it R, which is x squared plus y squared squared root. The world line of this particle is obviously R of t is simply a sine wave. Okay? Now, the second problem is interesting because it's not entirely clear that the same dynamical situation could give rise as a solution to both a circular motion and also a harmonic motion, but gravity does. Okay, this 1 over r squared does. There are a lot of very nice properties of 1 over r squared. And in fact, if you take orbit at the surface of the Earth, radius r, and you also at the same time let somebody draw through this tunnel, you can solve for the tunnel motion, and you can see right away that it's harmonic motion, right? And also, the period will be exactly the same as this orbit. So it goes like this. Okay? Now, there's just, if you look at the projection, now this, if you look at it over here, is just a circle, okay, in this projection. If you collapse this down, project it onto the xy plane, it's simply a circular orbit. Stretch it out along the t-axis, and you get a helix. And if you look at it along this axis, you can see a sine wave. Okay? If you project this, if you had a light casting a shadow on a page over here, right, you would see just a sine wave. All right, so it's the same solution. You have a circle, a helix, and a sine wave. Okay. All right, so obviously when you have in gravity, you have r double dot equals 1 over r squared, or gm over r squared. So you have taking the second derivative with respect to time brings you back to r, but with r squared on the bottom in the denominator. Okay, so the solution to that will be to the 2/3. All right, the first calculation was simply showing that the second derivative gives you the same thing, but inverse squared. The function x to the 2/3, when you take a derivative twice, it gives you x to the 2/3 again, but in the denominator squared, or t to the 2/3. And again, we're going to see that, you'll see that in cosmology, and you'll see that also in Big Bang collapse. The world line of a circularly orbiting particle is obviously a helix. It's just going like this, okay? The world line of this particle is obviously, r of t is simply a sine wave, okay? And the world line for the other particle is whatever, x to the 2/3, some like a parabola kind